Alright, so the next thing we want to talk about, which is really the whole reason why we want to talk about combinatorics at all. I mean, other than the fact that I think combinatorics is quite interesting, how you can ask these relatively seemingly simple questions about how to count various things. And it turns out to be somewhat complicated, and you actually need a sort of rigid logical structure in which you can apply some seemingly simple rules in more complicated ways. And, you know, I think it's sort of interesting on its own, but I kind of do this for a living, so, you know, it makes sense that I would enjoy it. Now, the real reason why we're getting into it is probability. All right, and I've given a sort of loose definition of probability here. And what it is it's the mathification, if you will, the quantification of chance, likelihood, and expectation. All right, so I've just given you some very simple and straightforward examples down here that we're going to go into detail about throughout this video. Some simple examples. The simplest one you can really think of is flipping a coin. You know, you've got a coin. It's either got heads or tails. You flip it, and you can quantify the likelihood that it will show up as heads, and quantify the likelihood that it will show up as tails. Rolling a die. Here, die is just a singular of dice. And the idea here, if it's a standard six-sided die, right, this is just a, little cube. If we were in class, I would bring an actual die with me, but these are the times we're living in. So, it's a die. It's got some number of pips on it. That's what these dots are called. By the way, fun trivia for you. Those are called pips. Anyway, you've got your standard six-sided die. Rolling this die, what's the likelihood that you get a 1 or a 2 or a 3 or whatever? You can ramp this up to 2 dice, right? So this is like, if you play a lot of board games, very often they'll have you roll 2 six-sided dice and use the outcome to do whatever. Move your piece however many spaces, for instance. Or if you're into games of chance, betting games, craps, for instance, is played by rolling 2 dice. And the most interesting of these sort of straightforward examples is definitely this one, dealing cards. And the reason why it's the most interesting is because in the past examples that we've been looking at, you've seen just how many different combinations of cards there are out there. In building up these 5-card poker hands and in counting, the number of pairs and the number of flushes and so on, there are a lot of hands out there. And the way that, if you ever watch, well, this is sort of outdated now, but, 10 to 15 years ago, the World Series of Poker was a really popular thing on TV. It was shown on ESPN all the time. And if you ever wonder how the final table at the World Series of Poker was almost always, it's 9 players, but it's almost always like 6 of the same people every single year at the final table. And if you ever wonder how people can end up so consistently at the final table in what amounts to a game of chance, because poker is just based on dealing cards and, the odds of you having a better hand than your opponent in some sense. If you ever wonder how they're able to do that, it's because they have a phenomenally good understanding of the probabilities of various hands. And so they know, they have sort of a running tally in their head of how committed they are to every hand based on how much money they've already invested by betting or anteing or whatever the case may be. Versus the probability that their hand, the actual cards they have, is actually the strongest hand at the table. So this is all, a sort of rapid-fire way of doing probabilities. There's also this idea of counting cards. This applies more to something like the game of blackjack. And if you have a very strong understanding and an extremely good vivid memory, then it's possible for you to have a running tab of the probabilities that you are going to draw, something less than 7 so you don't bust in a game of blackjack. All right, so if you don't know the rules of blackjack, then what I just said made absolutely no sense. That's okay. Anyway, so these are just some simple examples that we'll go into a little bit of detail about. Now, I want to give you some idea of the big picture here. It's way more than just gambling games, of course. That's not why we care about probability. The simplest example that you see every single day if you ever check the weather report is meteorology. This is the sort of biggest application of probability to everyone's everyday lives. All right, when you open up your weather app and it says there's a 5% chance of precipitation today, what does that actually mean? How did they come to that number? How are they possibly quantifying the percent chance that it actually rains? It either does or it doesn't. But what does that 5% actually mean? We can get into that a little bit. So meteorology is a huge one. Predicting weather patterns with certain, basically not just saying what is and is not going to happen, but rather saying how likely it is that various things will happen, like rain or snow or a hurricane or a tornado or what have you. The next one on the list here, actuarial science. This is all kinds of insurance. Life insurance, health insurance, car insurance, home, renter's insurance, all of these things fall under the umbrella of what's called actuarial science. And why insurance companies are able to make money when they are effectively playing a game of chance is because they have a very good understanding of the likelihoods of various events happening, and they price their insurance plans based on an understanding of the likelihood that these events will happen in such a way that in the long run they are virtually guaranteed to make money. All right, this is really the idea. It's the exact same principle as to how casinos are able to run games of chance exclusively and still make a profit. All right, if you've ever wondered how that's possible, a very good understanding of probability is how it is possible. All right, moving into some slightly more interesting, or mathematically interesting, I should say, things. Finance is a big one. I call this one more mathematically interesting because typically you need to have an extremely solid mathematical foundation to move into finance. And this is like understanding probabilities related to the stock market, right? So what are the odds that a certain stock goes up by, I don't know, 5 cents in the next week, things like this. Bigger picture things, astronomy is an important one. Things like understanding when the sun is going to have massive solar flares and solar storms. Understanding the probabilities of asteroids having near misses or colliding with Earth. Things like this. Or even just small rocks hitting our satellites in orbit and needing to be repaired. So things like this come up in astronomy all the time. And far and away, the most abstract of all of these that I've listed is quantum mechanics. This is the physics of the subatomic. Right, so this is like understanding how electrons and protons and neutrons exist in our universe. Turns out to be an incredibly non-trivial thing, and one of the biggest breakthroughs in the history of humanity was something known as the Heisenberg uncertainty principle. We will not go into any details about this at all, but I wanted to mention it. Right, so the Heisenberg uncertainty principle. Principle. This basically says that I wrote uncertainty. That should be uncertainty. Loosely speaking, the Heisenberg uncertainty principle says that if you're looking at something subatomic, like an electron or a photon or a neutron or something, we can never know both its position and its velocity at the same time with 100% certainty. So what this says is that basically the best we can do for understanding how subatomic particles exist and move around is by understanding with a certain probability that they are where we think they are, or that they are moving in the direction that we think they're moving. So that's super bizarre. It's incredibly wild. If you want to Google that, the Wikipedia page probably is scary. I doubt it's written for the average reader. But, certainly Googling the Heisenberg uncertainty principle, I'm sure you can find some sort of pop science things that have been written about it, because it's kind of fun to read about. Okay, so these are like really big picture things where probability is not only important to the field, but absolutely essential. Right, so these are fields upon which, they have really been built upon probability. Okay, so let's just do some very simple examples. All right, example 1. Let's say you have a fair coin. This is going to be a thing that I refer to a lot. When I say a fair coin, I mean it's got two sides. And I don't want any weird 3-sided, 4-sided coins you might have seen. It's got two sides. We will always refer to them as heads or tails, H or T for short. And this word fair means that both sides are equally likely to occur. Right? It's possible to have a weighted coin, an unfair coin, where heads. The coin was minted in such a way that heads or tails, either one, is slightly heavier, and that's going to make. If you've ever dropped something that's really top heavy, the top heavy part tends to fall down to the bottom. It tends to fall. The thing tends to right itself in midair so that the heavy part falls first, and it tends to settle with the heavy part on bottom. Things like this. So these unfair coins will land in a way that is biased toward heads or tails, and this is a way that carnies will grift you out of your money. Again, that's a pretty dated reference. I'm not sure how many carnies are peddling unfair coins these days, but who knows what you kids are into. So let's say we have a fair coin. Right, this means that heads and tails are equally likely. And what we're going to do here is say, okay, if they're both equally likely, right, H and T are equally likely. All right, so what that means is that there are only two outcomes for this coin. All right, that's another thing I'm assuming here. There are only two outcomes. You're not going to have, like a nickel, for instance. There's a non-zero chance that a nickel will land exactly on its edge. If you're looking at a nickel, it's got this like non-trivial side to it. It's never going to land on that flat side. Right? It's only going to land on heads or tails. Never in between. All right, so it's only going to land on one of two sides, heads or tails. That means that there are two outcomes. That are equally likely. Therefore, I would say the probability of heads excuse me, would be heads is one of the two outcomes that are there, and there are two possible outcomes total, and they're equally likely. All right, so I would say that since heads is one of those outcomes, right, it's just one of the two, and there are two total outcomes that are equally likely, heads should occur 1/2 of the time, in some sense. All right. So this is what probability means, and this is how we would denote it. Right. The way you read this is the probability of heads, which is shortened to H. All right, and it's equal to 1/2, and this is the number of H's that are on the coin. Right. There's only one H on this coin. And this is the number of outcomes total for the coin. All right, very simple extrapolation here. Probability of tails, right? This would be, well, there's one tail on the coin. So it's going to be 1 out of the 2 possibilities, either heads or tails. All right, exact same principle here is being used. There's one tail on the coin, and there are 2 total possible outcomes. Therefore, 1 divided by 2. All right, and I want you to notice a few things. The probability of anything, right, absolutely anything. Right, there are some basic principles that need to be true here. It will always be bigger than or equal to 0. Right, the least likely something can ever be to occur is having probability 0. What probability 0 means is that there is absolutely no earthly chance that that event will occur. All right? So, for instance, me being drafted by the 76ers at center has probability 0, right? I'm 5'6" and I'm terrible at basketball, right? So this is just not going to happen. So that is an example of an event that has probability 0. The sky suddenly turning rainbow colors for the rest of the universe's life almost certainly has probability 0, right? Can't imagine that's going to happen. All sorts of different things, right? Anything you can think of that you classify as absolutely unimaginably impossible would have probability 0, right? And on the flip side of that coin, pardon the pun there, because we're talking about coins, the most likely anything can be to occur, because we're viewing these things as fractions, right? It's like how many events of a certain kind out of how many total events there are. Well, the most likely something could be to happen would be what we're going to call probability 1. All right, so all probabilities will be between 0 and 1. And you can see that up here, right? The probability of heads, 1/2. The probability of tails, 1/2, right? And let's think of some probability 1 events. Let's see here. This is things that will absolutely 100% occur. Let's see here. The sun is going to set tonight, right? This is, it's really not like probability 1, but it would require some universally catastrophic event to not occur. So I'm going to go ahead and say that that's probability 1, right? 100% chance that the sun will set tonight. The wind is currently blowing outside my window, so I'm going to say it's probability 1 that the trees are rustling outside my window, right? Things like this, all right? Things that are absolutely certain to occur. Okay, all our probabilities will always be between 0 and 1. If you're doing a problem and you get a number for a probability that is less than 0 or bigger than 1, you have made an error. Okay? No probability can be bigger than 1. No probability can be less than 0. There are some geese screaming outside my window. I hope you all heard that. Okay, so let's see here. These probabilities satisfy these 2 requirements, right? They're both between 0 and 1, so that's fine. And here's the other thing I want you to notice. Let's ask this question. What is the probability of heads or tails? All right, so here I'm going to be a real stickler about the language that we use because it's very important. The word or means something very specific here, right? You've got to be careful about what you're saying. So what we're asking here is you flip a coin, right? So if you've got a coin, great. If you don't, just imagine you're holding a coin. And let's say you flip this coin and you look at the outcome. Looking at the outcome just means looking at what's face up. Is it a head or is it tails? All right. What is the probability that what you are seeing after flipping this coin is either heads or tails? Either one, right? Well, unless your coin, after you flip it, spontaneously grows a third face, which is neither heads nor tails, this is a certainty. This is going to happen. You are going to see a head or a tail. Right? It's absolutely going to happen because you're either going to see the head side when it lands, or you're going to see the tail side. All right, so this is a guarantee because these are the only two possible outcomes. All right, so what this says is that this should be a probability 1 event. This is a certainty, right? It is going to happen. And let's see why this is the case. So we already saw an example of this in our counting lessons. When we use the word or, we're really talking about adding. Okay, so let's think about what we're saying here. We have the probability of one event or another event occurring. Well, heads is one of the events on our coin, right? Let's go back up here. Heads is one of the two events. Tails is the other event. By the way, outcomes we often call events in probability. So heads is one event, tails is the other event. So let's see here. We've got 1 plus 1 events, right? It's either heads is the first one, or means add. It's tails, which is the second event, divided by the total number of events that exist for this coin, which is 2. In other words, we get 2 over 2, and voila, this is a probability 1 event. All right? So this is the idea that's sort of at play here. Now, since we already answered an or question, I want to take it one step further. And let's just answer, the sort of complementary question to this. What is the probability of heads and tails? Now, and here means simultaneously. Right? So what's the probability that you flip this coin, it lands, you look at it, and you see both heads and tails? Right? That's the question. Now, hopefully, you agree with me that the answer here is that this is an impossible event. There's no way, unless your coin breaks or you've got an elaborate system of mirrors, there's no way you are going to see both heads and tails simultaneously when you flip this coin. All right, so this is an impossible event. This should be probability 0. All right, this is an example of an impossible event. Okay, so these are sort of the fundamental ideas behind what we're talking about here, with the simplest possible probabilistic experiment you could ever do. That's what these are generally referred to as, experiments. And this is one that has 2 equally likely outcomes. So let's look at another one. Let's say you toss a fair 6-sided die. I have to be specific and say 6-sided because, as anyone who has ever played Dungeons & Dragons knows, there are a lot of dice out there, from typically 4 all the way up to 20, although I have seen a D100 before. So anywhere from 4 up to 20 are your sort of traditional dice sizes. They have to have a certain number of sides, not just anything in between, but regardless, in order to be fair, anyway. that's a geometry problem that I'm not going to get into. So let's say you toss a fair six-sided die, and I didn't actually give you a question here. I should give you a question. Find the probability of rolling a 6, right, just as an example. Alright, so this means you roll the six-sided die, and the side with 6 pips, 6 dots, is showing on the top. Alright, again, fair here means that all 6, there are 6 outcomes, the numbers 1 through 6. Alright, so outcomes are the numbers 1, 2, 3, 4, 5, and 6. And fair means that they are all equally likely to occur. Alright, so probability of a 6. Well, look at your so-called sample space. Right, this is our sample space. It is the set of all possible outcomes. That's what sample space means. Right, so this is a sample space. Set of all possible outcomes. I just put curly braces around it to make it into a set. Just like with the non-sequential coalitions back before school was closed down. So you take a look at this thing and you say, okay, how many things in my sample space are 6s? Well, there's 1. Right, there's 1 6. And how many total things are in my sample space? Well, there's 1, 2, 3, 4, 5, 6 things. Since they're all equally likely, the probability of a 6 is 1/6. Alrighty, let's ask a more complicated question. By the way, 6 was not special here at all. This is the same as the probability of a 1, a probability of a 2, probability of a 3, probability of a 4. They're all equally likely, so their probabilities should all be the same. Probability of a 5, right? They're all the same. They're all 1/6. Alright, so let's look at something a little more complicated. What is the probability that you roll an even number? Alright, so this is a little more complicated than the coin example, just because you've got more options in your sample space. So let's look up here. How many even numbers do we have in here? I'll circle them in purple. We got 2, we got 4, we got 6. So there are 3 even numbers in our sample space, and there are, again, 6 total events. Therefore, the probability should be 3 divided by 6, which is 1/2. Right, and I haven't really been playing this up at all, but you can think of this as a 50% probability, right? A 50% chance that you roll a die and you'll get an even number as an outcome. Okay, I do want to take a second to view evenness as what we just said above. This means 2 or 4 or 6, right? Those are the even outcomes on this six-sided die. And so we could have written this as a probability of a 2, or a 4, or a 6. And let's just use the principle that we just used a second ago and say, okay, this is going to be the same since I'm using the word or in here. This, I don't want to do that. Hang on one second. I want to say that this is going to be the probability of a 2. Well, how many 2s are there in here? Right, there's 1, it's right there. There's 1 4 and there's 1 6. And say that this is the probability of a 2, which there's only 1 of those, plus a 4, there's 1 of those, and a 6, there's 1 of those. I'm adding, right? I'm saying or, so I'm adding. And this turns out to be 3 6 as well, right? That's exactly the same answer, just a slightly different way of getting there. All right, so again, this quantified up here, right? This number would be about 17-ish%. It's like 16.66666 repeating, I think. Right, so this is the rough idea of what you end up with. And translating these to percentages is possible because they're all numbers between 0 and 1, and so they can easily be translated to a percentage between 0 and 100%. All right, so we'll do some more complicated examples in the next video.